We now have two new tools to work with. We know about samples that represent their populations, and we know about simple probability. Now it is time to use those two tools together. Inferential statistics allow us to determine the probability that a sample mean represents the population from which it was drawn. Inferential statistics, also known as null hypothesis testing, use probability to determine whether a particular sample or test outcome is representative of the population from which the sample was originally drawn. If not, if the sample mean is not exactly the same as the population mean, that may be for one of two reasons. One, the sample mean may differ from the population mean because of chance, or B, the sample mean may differ from the population mean because of an effect. Probably an effect from the experiment we've just done on the sample. Remember that when we draw a sample from a population, we expect that the mean of the sample will be the same as the mean of the population. But when we do an experiment, we typically draw a large sample, which we then randomly assign into two groups. The experimental group is the group that is tested or given a treatment, aka the treatment group. The control group is a group identical to the experimental group, except that it is not given a treatment. Both groups are drawn from the same population, so they should have the same mean. If our intervention did not work, if the drug was not effective, if the education did not sink in, then we should expect that after the experiment, the sample mean of the experimental group would still be the same as the sample mean of the control group, both of which are the same as the population mean. In other words, nothing has changed because the intervention didn't work. But if, after the experiment, the sample mean of the experimental group is different than the sample mean of the control group, which didn't change from before the experiment, we then suspect that the intervention had an effect, and this is called hypothesis testing. A hypothesis is a testable prediction about a real-world phenomenon. I think this drug will lower blood pressure is a testable hypothesis. Experimental hypotheses propose a starting point that will then be accepted or rejected by examining the evidence that supports or contradicts it. If the evidence supports the hypothesis, we accept it as a good explanation. If the evidence refutes the hypothesis, we reject it as a poor explanation. Now later, I'm going to explain how we never really accept a hypothesis, but for now, we're going to use accept and reject for simplicity. There are two experimental hypotheses, the null hypothesis and the alternative hypothesis. The null hypothesis states that the sample mean is the same as the population mean, so any differences we do observe are due to chance. The alternative hypothesis states that the sample mean is not the same as the population mean, so any differences are due to an effect. We will examine whether the sample mean differs from its population mean. And of course, the sample mean will always differ from the population mean if you go out to enough decimal places. But anytime a sample mean differs from its population mean, there are then two possible explanations. A, the sample mean still represents the population mean, although it may be a poor representative, or 2, the sample mean represents a different population, also known as an effect. So imagine we have a population of people with high blood pressure. The diastolic blood pressure of the population is 102. Now, normal diastolic blood pressure is under 80. Diastolic is the bottom number of your blood pressure, systolic is the top number. We draw a sample from that population and we expect the sample will have the same high blood pressure as the population from which they were drawn. We measure them, and sure enough, they have high blood pressure, just as we expected. The diastolic blood pressure of the population is 102. the diastolic blood pressure of our sample is 102.5. But we say that those numbers are really the same. Yes, there was some random variation, but the sample mean represents the population mean plus a little random error. Because the sample mean will always differ from the population mean if you go out enough decimal places, the means are still pretty close. So the variation that we see is due to chance. Now we draw a second sample from the population. Likewise, we expect them to have high blood pressure, and sure enough, they do. Their diastolic blood pressure is 101. Again, the sample mean differs slightly from the population mean, but we conclude that the variation is just due to chance. Functionally, the means 102, 102.5, and 101 are the same. No difference. We're going to assign this first sample to be the control group. We're going to assign the second sample to be the experimental group. And really, for the sake of accuracy, let me add that to do an experiment properly, we would not actually draw two samples from the population. We would draw one large sample and then randomly assign those participants to one of two groups. In any case, we would still have an experimental and control group. But then we give our experimental group a new drug that is supposed to lower blood pressure. We keep them on this drug for 2 months, and then we measure their blood pressure again. After treatment, we find that the control group mean changed slightly from 102.5 to 101.2, but they still have high blood pressure. This variation was due to chance, and the control group mean still represents the population mean. But the experimental group sample mean is lower than it was 2 months ago. Before the experiment, the diastolic blood pressure of our sample was 101. Now it is 86. Now we suspect that the sample mean represents a different population, the population of people with normal or close to normal blood pressure. And our explanation for why the experimental sample mean is now so much lower, the drug had an effect. It lowered blood pressure in the sample. We suspect that the experimental group sample mean now represents a different population, the population of people with normal blood pressure, whose diastolic blood pressure is under 80.